Thank you. So this is joint work with my advisor, Irit Dinur. So let me start with an example that I hope that at least some of you already know. So imagine your favorite finite vector space V, and suppose that somebody is trying to give you a low degree function on this vector space. But instead of giving you a whole function, they're actually giving you pieces. So for every line in this vector space, they're giving you a low degree function f of L that's defined only on the vertices of this line. So if we know that these lines are consistent with one another, namely that for every two lines that intersect on a point, the two local functions assign the same value to the point, then we know that there exists a low degree function on the whole space, so that all these functions on lines are actually just restrictions of this global low degree function. The question that interests us today is what happens if these functions on the lines are consistent only 99% of the time. So in this case, and this is a beautiful theorem by Rubinfeld and Sudan from the mid-90s, we can still find the low degree function G so that most of the lines are still restrictions of this low degree function. About a year later, Goldreich and Safra proposed a more general setup to this question. So now V is no longer a vector space, it's just some finite set of vertices. And instead of lines, we just have subsets of these vertices. And for every small subset, we're given a local function that's defined only on the vertices of this small subset. And now our test, instead of picking two lines that intersect in a point, is just as follows. We sample two sets that intersect according to some known distribution, and we check whether our local functions agree on all the vertices in the intersection between the two sets we sampled. So again, we can try to ask the question, what happens if our family of functions agree with one another 99% of the time? And what we want this time is to just find any function on the whole vertex set so that most of these local functions are actually restrictions of this single global function. But of course, this is not always possible. The answer depends on the specific set system we take, and of course, the distribution inside the agreement test. So let's look at a silly example. Suppose we have this set system with 6 vertices, 3 sets, and the family of functions is given in the slide. Our agreement test, let's say, could either sample S1 and S2, or sample S1 and S3, each with equal probability. So notice that if we were to sample S1 and S2, our test would reject simply because the two functions don't agree on the assignment to the vertex number 1. However, if I were to sample S1 and S3, our test will accept because both of the functions agree on what they say to vertex 5. So what can we say here? I don't know. More formally, the requirement we want from this agreement test is it to be sound, namely that if we have any family of functions that pass the test with probability 1 minus epsilon, which we should think of as like 99%, then we would be guaranteed a function on the whole vertex set so that 1 minus O of epsilon, 98%, will actually be restrictions of this global function. So here the O notation hides a constant, and of course this maybe only makes sense if we're not looking at one set system, but a whole family of them. But this is technicalities that I don't want to get into. So what are the results that we had? Essentially, we found sufficient criteria for set systems to have sound agreement tests. And these sufficient criteria are given in a spectral sense. What we actually do is we take the set system, we derive from it a bunch of graphs, and if all these graphs are expander graphs, then this will imply that our set system has a sound agreement test defined on it. a reason this is good is because agreement testing is sort of a hard combinatorial property, and testing and verifying that some graph is a spectral expander is something that a lot of times we have more tools to do, and we can do it more easily. So indeed, this result immediately gave us new set systems where we actually can show that we have sound agreement tests on. So one example is high-dimensional expanders. And for those of you who weren't in Tali's tutorial, I'll just say that these are essentially sort of the hypergraph equivalent of expander graphs. We also got agreement tests for balls in some expander graphs, matroids, vector spaces, and many new and interesting set systems, and some not so new. But before I go any further, I want to address the question, where do we actually see these agreement tests, say in PCPs and constraint satisfaction problems? So I want to give an example and describe a way we can use agreement tests to actually reduce CSPs where we query D variables to CSPs where we query only 2 variables. So what do I mean by this? Suppose we have a set system, which is a CSP, and every set here is of size D. And what do I mean by CSP? For every set, we have a constraint that regards only the vertices in this set, and it tells us which assignments on these vertices are legal and which are not. So those of you who aren't that familiar, we should just think of DSAT or some problem of the sort. The goal of this is to find an assignment to the whole vertex set that satisfies all or sometimes most of these constraints. And in general, this problem is NP hard, even if we want to find a satisfying assignment to just most of the constraints. However, of course, if I look at only a single set and a single constraint, it's much easier to find a local assignment that satisfies just this constraint. Now imagine that on our set system, we also have an agreement test. So in this case, even if I could find the local satisfying assignments that satisfy the local constraints, if I were able to do this in a way that was consistent according to my agreement test, then this will already imply that I could find a global assignment that agrees with most of these local assignments and therefore satisfies most of the constraints. So in essence, this seems like a task that is almost as hard as just finding this global assignment. So indeed, after describing this, our new CSP, which will have only 2 queries, our new variables will be a variable per each set inside S. The new alphabet should be interpreted as functions that are local assignments to these sets. So our alphabet probably grew a little. And our new constraint is just to sample a constraint according to the agreement test and check whether the 2 assignments are actually consistent with one another. And of course, to check that the local assignments are also legal according to the old constraints. And this new CSP still retains almost the same hardness as the old one, because if I find a satisfying assignment to the new CSP, this means that I found satisfying local assignments to the old CSP that also agree with one another. And as we said before, we can find from this a satisfying assignment to the whole vertex set in the old CSP. So in fact, a very similar reduction was used in the combinatorial proof of the PCP theorem. And agreement tests are also seen in other PCP constructions, such as the parallel repetition, or with another soundness guarantee, the 2-to-1 gains. And they also have other applications, such as finding robust locally testable codes, and more and more. So I want to get back to the question, which set systems actually give rise to sound agreement tests? Here I think is a good place to mention some previous results. A lot of previous results actually took a specific set system or a specific family of set systems and proved ad hoc that they admit sound agreement tests. So you can see some references here. One I want to mention in particular is a result by Dinur and Kaufman in 2017, where they showed sound agreement tests on a slightly broader family of set systems that come from high-dimensional expanders that also satisfy some technical requirement. And these high-dimensional expanders, the nice thing about them is that they are very sparse, meaning that every vertex is contained only in a very, very small and fixed number of sets. And it might be hard to believe that there could even exist a sound agreement test in this setting. And the novelty in their work was that they somehow swapped sort of density arguments that were used in previous works to arguments that actually use spectral expansion in some local graphs that they found in these high-dimensional expanders. So with this in mind, we come back to our question, and when we approached this, we eventually found out that what we're trying to do is to find sort of the right local spectral properties that we can require from any arbitrary set system, so that if these local properties indeed occur, then our set system will have a sound agreement test. And indeed, we found this following theorem, that a set system that satisfies some local spectral properties indeed gives rise to a sound agreement test. So let me, in the next few slides, just demystify a bit what I mean by local spectral properties. There's a very basic notion in testing called the test graph. And in our context, the test graph of some set system with an agreement test is just a graph whose vertices are the sets in our set system. And I draw an edge between a pair of vertices if I can ask about them in my agreement test distribution. So in our example from before, we have 3 sets that correspond to the 3 vertices. And since I can sample S1 and S2 or S1 and S3, I draw edges between the appropriate vertices. This graph seems to remember everything or almost everything about the agreement test, but spectral expansion of this graph is sort of not enough, and we can sort of construct counter examples where this graph is like even a decent expander, and still we won't have sound agreement tests. So somehow we need to refine this notion of the test graph and to look at local variants of it. So here I define the local test graph, which is just a subgraph of this test graph that consists only of sets that contain some fixed vertex. I'm sorry, this B there should be a V. So in this example, if we take the vertex number 5, its local test graph it just consists of the sets S1 and S3, who are the ones that contains actually this vertex 5. And when we say local spectral properties in the theorem, what we mean that these local test graphs should actually be good enough expander graphs, good enough spectral expanders. I've put in an asterisk here because actually when we prove this theorem, we need sort of other variants of these graphs that are slightly more complicated, and I won't describe them here. But in essence, this is what we want. So finally, I want to give you a very, very rough and simplified proof sketch to our theorem. So what we have is a set system where we assume these local test graphs are well enough expanders, and also a family of functions that passes this agreement test with high probability 1 minus epsilon. What we want is to find a global function on the whole vertex set so that 1 minus O of epsilon of these local functions are actually restrictions of this global function. The global function that we choose is a very natural one. We just take the majority, meaning for every V, I look if the local functions assigned to it, if more local functions assigned to it 1, then the global function will assign 1. If more assign 0, then the global function will assign 0. It's just the majority vote on the vertex. So how will I prove this? A first step, I like to call it a smoothing step, or maybe a decomposition step, where I passed from a statement about agreement with probability 1 minus epsilon on the whole intersection between a set, to a statement about, which gives us very, very strong agreement, okay, y minus O of epsilon over the size of the set S, which should thought of as much smaller than 1 minus epsilon. But here, I don't require agreement between agreement on the whole intersection, just a randomly picked vertex in this intersection. So let me just phrase this again. I pass from a statement about agreeing on the whole intersection with high probability to agreeing on a single randomly picked vertex, but with very high probability. So in fact, we can't get this statement as I wrote it here. We actually need to do some massaging to these functions, and actually there's also like a small number of functions that we need to throw away. But essentially, we want to pass to a statement on single vertices. And this statement is enough, because if I will show that these local functions agree on a randomly picked vertex with this global majority function, then by a simple union bound, I can imply the guarantee that I needed for my theorem that, that most of these local functions agree with the global function on the whole domain. So this is a union bound, and you can try it. It's not a very hard exercise. And the reason that we're doing this smoothing step is that once we pass to a statement on the vertex, it will be much easier for us to actually argue about this vertex using its local test graph. So the second step, I like to call it the pasting step, is where we use the expansion of the v-test graph to show that if our functions agree on this vertex with very high probability, then we can show that most of these functions agree with the majority, also with very, very high probability. Let's see why. So let's fix a typical vertex here and look at its local test graph. And in this test graph, we construct a cut where on one side of the cut, we put all the sets whose local functions agree with the majority. And on the other side, of course, the sets that disagree with the majority, namely the minority. Okay? This cut has very few edges crossing it. Why is that so? So just recall that from the previous step, we actually have the statement that most of the pairs of sets actually agree on the assignment to this vertex. So any edge that crosses this cut corresponds to two sets whose local functions actually disagree. So what we see is that we have very little number of edges here. So we have an expander graph, and we have a cut with very few edges. This in expander graphs can only happen if one of the sides in this cut is very small, because one of the ways to actually define expander graphs is that cuts that correspond to large sets on both sides must have many corresponding edges. So this is the contrapositive, which means that one of the side of the cut must be very small, and obviously this can't be the majority, so it must be the minority. Thus, in this case, we've managed to prove that our local functions mostly agree with the majority. Good. Let me just end with some open questions. So the first thing that interests me is to refine this result. We only gave sufficient conditions, but it would be very interesting to see if we can also show a necessity of conditions that are maybe differently phrased, maybe even simpler. The second thing that interests me is what happens, not if we're promised that our functions pass the test 99% of the time, but we're only guaranteed that they pass the test with probability, which is slightly above what we maybe could expect from a random assignment of functions. This question, I think, is more open. And finally, of course, we'd like to find maybe more interesting set systems with agreement tests that maybe we can use them to construct new and improved PCPs somehow or other applications. So thank you very much. Yes, Oded.
So I was wondering, I didn't get it
Okay.
So it's not clear to me if it implies that the system that Muli and myself used satisfies this condition or not.
So the set system that you used satisfied sort of a weaker condition where we don't require sort of agreement, like complete agreement on the whole domain, I think, but just sort of approximate agreement, like say on 99% of the domain or something like that. So there are, I should say, there are other soundness requirements that we can ask for, and our paper actually addresses some of these things. I only included like the basic one. No, I just did it to simplify. It's not important.
More questions? Okay, let's thank the speaker again.
Thank you.